In the darkened belly of the Channel Tunnel, two rail tunnels stretch underneath the English Channel, transporting Eurostar trains, bringing life and commerce between England and mainland Europe. Yet, between them, an unassuming, lesser-known tunnel runs parallel, a service tunnel that seems benign on the surface but serves a purpose far more vital than mere maintenance access. In a fire scenario, it becomes a vital safety sanctuary, a corridor that protects lives. Its engineered whisper of pressure deviates from what travelers expect, revealing a crucial element of design hidden just beneath their feet. But why does this expansive tunnel network require a third tube that carries no passengers? Why invest in such a structure when it seems like an unnecessary expense? As we unravel this mystery, we will discover a fascinating world of engineering that ensures safety and efficiency beneath the waves. The Channel Tunnel, often dubbed the Channel, is a remarkable feat of engineering that has connected two cultures since its opening in 1994. Spanning a total length of 33.5 kilometers, it rivals some of the greatest infrastructure projects ever completed. Within its depths lies an ingenious system designed to manage air pressure, smoke, and emergency evacuations while allowing the swift movement of trains. The need for a third tube, however, shifts the conversation from sheer transport efficiency to life-saving engineering measures. Central to our understanding is the critical role of air pressure inside the tunnels. The service tunnel maintains a higher air pressure than the two rail tunnels. This difference in pressure creates a continuous outward airflow directed through strategically placed cross-passages. During a fire emergency, this outward airflow acts as a powerful barrier, preventing smoke from invading the rail tunnels and providing a vital escape route for passengers and crew. Let's explore the mechanics behind this pressure differential. Air pressure is defined as the weight of the air above a certain point, exerting force per unit area in all directions. At sea level, the average atmospheric pressure is about 14.7 pounds per square inch. By maintaining a slightly elevated pressure in the service tunnel, engineers create a protective buffer zone. For example, if the pressure in the service tunnel is set at approximately 0.2 bar above atmospheric pressure, it means that the air within is subtly pushing outwards. This creates an unyielding shield against smoke and harmful gases during a fire. Without this engineered pressure, how effective would any evacuation plan truly be? Human lives depend on systems like this working seamlessly. In an unfortunate event, if a train were to experience a fire, smoke can spread rapidly. Statistics indicate that smoke inhalation is responsible for around 60% of fatalities in tunnel fires. Thus, every detail in the design of the tunnel's infrastructure, like the service tunnel, becomes paramount. Cross passages, placed at intervals throughout the tunnel, connect the rail tunnels to the service tunnel. There are around 15 cross passages embedded within the tunnel structure. These short access points, located approximately 250 meters apart, allow people to move into the service tunnel without having to travel through the smoke-filled rail tunnels. They are doorways to safety. In the event of smoke filling the rail tunnel, these passages become essential lifelines. On average, it would take a person just a few minutes to walk the length of one of these passages, and during this time, every second could make a critical difference. Now imagine you're on a train hurtling toward a tunnel. As you travel, you might see the gleaming walls rushing past, each second drawing you closer to the vast expanse beneath the English Channel. If a fire were to break out, what you might not realize is that you are surrounded by an intricate network, working tirelessly to protect you from harm. You may be wondering, why not use a standard smoke evacuation system like those found in typical buildings? The answer lies in the sheer scale of the Channel Tunnel. Engineers needed a design that could withstand the unique challenges of a long, confined space with high volumes of traffic. In fact, the sheer length of the tunnels, over 53 kilometers when combined, necessitated the use of dedicated systems that conventional designs could not sufficiently accommodate. Around the midpoint of our exploration, consider this: which of these engineering marvels would you least want to find yourself standing next to in an emergency? Would it be an enormous airliner on a tarmac preparing for takeoff, a freight train moving through a dark tunnel, or a massive crane lifting heavy cargo high above? Write your thoughts below. While we often consider tunnels simply as passageways, engineering intricacies reveal vast, complex systems designed to protect us. Most people assume conventional escape routes and ventilation designs are sufficient, thinking perhaps it's enough to have a few emergency exits and some fire extinguishers. However, the presence of this service tunnel and its engineered pressure differential emphasizes a stark contrast to the reality. When contemplating safety, one cannot solely rely on traditional measures. In fact, it is the very existence of this third, seemingly superfluous tube that serves to undermine our common assumptions about safety. If most people believe that smoke prevention is merely a function of smoke detectors or fire extinguishing systems, they would be mistaken. Smoke control in tunnels requires a multifaceted approach that includes pressurized zones, tunnel geometry, airflow management, and dedicated evacuation pathways. Take, for example, the infamous Mont Blanc tunnel fire of 1999. A tragic incident that resulted in the deaths of 39 people, it underscored the dire consequences of inadequate smoke control measures in confined environments. The lack of a dedicated service corridor and an efficient smoke control system hampered emergency response efforts. The Channel Tunnel, having learned from such tragedies, is designed to be a different kind of structure, one that elevates human safety above all else. Let's wrap our minds around this critical point. The Channel Tunnel wasn't designed to merely facilitate rail travel. The hidden engineering that researchers and engineers built into the service tunnel encapsulates the vital need to ensure safety where the stakes are extraordinarily high. It confronts the ever-looming potential for disaster with layers of intention and foresight. As we conclude this exploration of the Channel Tunnel's service tunnel, it's striking to reflect upon the scale and complexity of engineering hidden beneath the surface. The attention to pressure, airflow, and how they interconnect reveals deeper insights about our built world. Each giant machine, every massive structure, is a testament to human ingenuity and a reminder of the unseen engineering that ensures our safety and efficiency. So, the next time you travel through the channel, consider the power of the invisible engineering that surrounds you. Recognize the unassuming service tunnel that dedicates itself to safeguarding thousands of travelers, delivering them safely to their destination. In the world of engineering, every giant machine hides one piece of engineering nobody notices. Subscribe for the next one, and tell me below which machine you want taken apart. Beyond the immediate understanding of the service tunnel's function, let's delve into the broader implications of its design, exploring the intricate mechanisms that sustain not only the safety of the Channel Tunnel but also the effectiveness of the entire transportation system that connects nations. One of the key engineering elements in maintaining safety and performance in tunnels like the Channel is the design of the ventilation systems. In the Channel tunnels, engineers have incorporated advanced ventilation systems that work in tandem with the pressure differentials. These systems are engineered to adjust automatically based on the thermal conditions and air quality inside the tunnel. With the rail tunnels carrying Eurostar trains at speeds of up to 160 km per hour, the air flow must change dynamically to ensure optimal conditions for both efficiency and safety. Imagine, as a train speeds through the confines of the tunnel, that it is stirring up air just as a ship moving through water creates waves. The air in the tunnels must be continually adjusted and monitored to prevent the buildup of smoke and toxic gases. This is accomplished through strategically placed ventilation shafts throughout the channel. These shafts facilitate the extraction of smoke while drawing in fresh air, maintaining an environment that is both breathable and safe. For example, in the event of a fire, conventional wisdom might lead one to assume that letting smoke escape through openings would be sufficient. However, the channel system is engineered with a series of smoke extraction systems that activate in real time to counteract airborne threats. When a smoke detection sensor is triggered, the nearest ventilation shafts begin to function at full capacity, effectively pulling smoke from the tunnel at a rate of approximately 100,000 cubic meters of air per hour. In contrast, typical smoke evacuation methods in other structures do not account for the same volume of air flow, especially over long, linear distances such as this. The lesson learned from the catastrophic fire events, such as the one that occurred in the Channel Tunnel itself in 2008, emphasizes the critical need for an integrated approach. In that incident, a truck caught fire in the tunnel. Emergency services were able to respond quickly, aided by the infrastructure designed to manage smoke. The successful extraction of smoke was a testament to the carefully implemented systems making powerful use of that pressure differential. The ability to create safer environments through foresight and design conscientiously informs modern tunneling practices around the world. Beyond ventilation, the service tunnel also plays an essential role in maintenance and inspection, ensuring the rail tunnels remain in optimal condition. Regular inspections are critical to maintaining safety and functionality. The design of the tunnel allows for maintenance vehicles to access the service tunnel at periodic intervals, executing repairs and scrutinizing structural integrity without disrupting the flow of passenger services. A notable engineering feature incorporated into the tunnel's service tunnel design is the sloped flooring, which is not only practical for maintenance vehicles but plays a part in the drainage system. Water accumulation in tunnels can create hazardous conditions. The service tunnel contains a drainage system equipped to handle rainfall and leakages effectively. Engineers designed it with gradients that encourage water to flow to designated drainage points, avoiding stagnant puddles within the service corridor. This dual-purpose design of the flooring addresses not only immediate safety concerns but also long-term infrastructure preservation. Although less visible, features such as the drainage system prevent damage to the tunnels and ensure that maintenance operations can continue without impediment. As we consider the infrastructure of the tunnel holistically, it becomes clear that every component serves multiple functions, addressing both everyday operations and extraordinary situations. There is a wisdom in this multifunctional approach to infrastructure design. The unexpected need for redundancy and resilience is an essential lesson for engineers and architects alike. Tunnels around the world, both modern and historical, provide case studies that showcase differing philosophies on structural safety, some of which have led to tragic consequences. In contrast, the Channel Tunnel was constructed with a persistently active mindset towards safety and operational excellence. A poignant example of this philosophy can be seen in the Gotthard-based tunnel in Switzerland, currently the longest railway tunnel in the world, which also features these types of safety redundancies. With a total length of 57 kilometers, this engineering marvel includes several very structured escape routes, emergency stations, and parallel emergency tunnels. Each design decision echoes the lessons learned from previous tunnel incidents, showcasing how engineers have built upon past knowledge to innovate for future safety. Consider the impact of such integrated engineering approaches globally. From the lessons of the Mont Blanc incident, where a lack of effective smoke control led to fatalities, to the resilient design of the Channel Tunnel, it is evident that there exists a shared responsibility among engineers to confront the risks associated with subterranean transit. As we draw a line from these historical events to the present, we see that the face of tunnel engineering is evolving, continually adapting to new threats and challenges. The tunnel stands as a beacon of what is possible with foresight, planning, and relentless attention to safety protocols. Now let's return to the original premise, the need for a service tunnel that carries no passengers. It is easy to dismiss such a feature as a luxury or even unnecessary. However, in the world of high-speed transportation infrastructure, luxury translates more accurately to vigilance and resilience. The service tunnel exemplifies the investment in safety that stems from an engineering philosophy that prioritizes human life over simple logistics. As travelers glide through the tunnel, they may not be aware of the unseen forces working diligently to keep them safe. It's an intentional design, quietly operational yet profoundly significant. The elongated tube, housing critical aspects of safety management and engineering foresight, creates a metaphorical dam against chaos, guarding against the dangers that a fire might unleash. Reflect on how this encapsulates the essence of modern engineering. Gigantic machines, sprawling infrastructure, and intricate designs operate with a singular goal, to ensure the safety and comfort of those who rely on them. From the air pressure that holds back smoke to the maintenance that prevents disaster before it strikes, these features weave an invisible tapestry of security we take for granted. Wherever you find yourself navigating through urban landscapes or speeding along rail lines, keep in mind the hidden complexities just beneath your feet or around your walls. Whether it's a humble service tunnel or a monumental bridge, these solutions reflect centuries of engineering wisdom dedicated to preserving lives and enhancing efficiency. The Channel Tunnel embodies the notion that every layer of engineering is a testament to human diligence and ingenuity. With each advance comes not merely the promise of improved transportation but also a resonant commitment to the protection of those who traverse the 33.5 kilometers that connect cultures and economies. As we close this exploration, it's striking to reflect on the magnitude of engineering hidden beneath the surface. The combination of air pressure management, advanced smoke ventilation, and structural integrity maintenance encapsulates our deep-rooted need for safety in motion. As the unseen threads of engineering and design weave through tunnels around us, they assert an unwavering commitment to human life. So next time you embark on a journey through the wonders of infrastructure, remember the service tunnel silently supporting your trip beneath the sea, tasked with defending your safety against the unpredictable. Every giant machine